I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss a few basic terms that are involved in laser. Yesterday we have seen some few important phenomena, and today we are going to discuss the rest of the terms after recapitulating what we have seen in the previous lecture. So, coming to part 1 laser, we have already seen the introduction to laser and we have discussed the terms stimulated absorption, spontaneous emission and stimulated emission. And today we are going to focus mainly on understanding what metastable state, population inversion and lasing action are. Now, when it comes to today's topic for discussion, we will be discussing the basic terms metastable state, population inversion and lasing action. So, what is a laser device? A laser device emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. So, whenever we talk about laser, what we see there is optical amplification, and this optical amplification is based on stimulated emission of radiation, that is electromagnetic radiation. Now, the term laser originated as an acronym for light amplification by stimulated emission of radiation. So, we'll see what laser stands for. What is the acronym for laser? L stands for light, L. A stands for amplification, which is denoted by A. And S stands for stimulated, and E for emission and R for radiation. So, we have got laser from light amplification by stimulated emission of radiation. Now, coming to the characteristics of light, the characteristics that make laser very important and which has brought in lot of applications are high monochromaticity. Mono is always related to single, chromaticity is related to color. So, it has a light of single color, or I say it is single wavelength. If you see ordinary light, they will have many wavelengths, different frequencies and different energies. But whereas laser light is highly monochromatic, means it is a light of almost a single wavelength. Then comes the high degree of coherence. When we talk about coherence here, coherence is always related to phase. Phase here means the state of vibrations of the particles. So here, high degree of coherence means whatever light that is emitted by laser will be coherent. It will be in the same phase. Then high directionality. Directionality means I can say it is unidirectional. Means whatever light that is emitted by laser travels in almost a single direction and with minimum divergence. That is also very important. If you see ordinary light will spread after emitting from the source. It may spread in different directions, but whereas laser light is going in a single direction, we say it is unidirectional with minimum divergence. Then comes the high brightness. Brightness is always related to intensity. If the amount of light that is emitted per unit area, per unit time is more, then it is bright. So, it is very bright. So, the laser light when we take compared to ordinary light, it is very bright. So all these characteristics make laser very unique and special. Now the first phenomena we are going to see is stimulated absorption. So whenever we talk about absorption, we have only stimulated absorption because the atoms cannot go into a higher level without absorbing the energy or without we supplying any energy. That is why we always call it as stimulated absorption. So what is happening in absorption? If a photon of energy h nu 12, that is what we are talking about h nu 12 is E1 is the energy of the ground state, E2 is the energy of the excited state. If we can supply the difference in energy between the two states with the help of a photon, we always talk about the energy of the photon in terms of E is equal to h nu. So when we are stimulating it, we stimulate it with the help of a photon, and the energy of the photon is given by E is equal to h nu, and this frequency must be suitable for the electron to transit into the higher energy state. So for that, what we mentioned here is 1, 2, means the difference in energy has to be supplied for the atom, so that what happens when this photon collides with the atom present in the ground state, which has energy E1, then the atom completely absorbs the incident photon and makes transition to the excited state. This is what we see in stimulated absorption. Now let us see in the diagram. So we have two different states. We have E1, which we call it as the ground state. E1 is the ground state. And then we have E2, which we call it as excited state or higher level excited state. So E1 is the ground state, E2 is the excited state. Now where are the atoms? The atoms are present in the ground state. Here we have seen atom present in the ground state of energy E1. So the energy of this atom is represented by E1. Then what happens when a photon is incident? When a photon collides with this atom, what is the energy of the photon? The energy of the photon is given by E is equal to h nu 12. We have to supply a minimum energy, which is the difference between the two levels, for this atom to make a transition into the excited state. So this is the photon that is incident. We call it as incident photon. Or I can say it is the stimulation that we are supplying to this atom. Now what happens when this incident photon collides with the atom in the ground state? So what is happening here? The atom will go to the excited state. So from the ground state, after absorbing the energy from the incident photon, it will be able to go into the excited state. So there is a transition that is taking place from ground state to excited state. So it absorbs the incident photon and makes a transition to the excited state. Transition is nothing but a movement from the lower level to higher level in this case. Now coming to spontaneous emission. An atom which is initially present in the excited state makes transition voluntarily. Voluntarily means on its own, or we can say spontaneously, without the aid of an external stimulus or agency, to the ground state and emits a photon of energy h nu is equal to E2 minus E1. Now what we are seeing here is exactly the opposite what we have seen in absorption. So what we have here is E1, which is the ground state. Then we have E2. This is the excited state. So after the photon is incident, the atom which is in the ground state has absorbed the energy and now it is in the excited state. The atom is now in the excited state having energy E2. Now, this atom cannot stay in the excited state for a long time. The time for which it can stay in the excited state, we call it as lifetime. The period of stay of the atom in the excited state is called the lifetime. And once the lifetime is over, this atom comes to the ground state on its own without supplying any energy or without the aid of any stimulus. This atom is going to come or make a transition to the ground state. This is how it happens. So this atom which is in the excited state is coming to the ground state on its own. Then what happens? A photon of energy where the difference in energy, now it is at a higher level having energy E2 and E1 is the ground state which is a lower level. So the difference in energy is being emitted. So H nu is equal to E2 minus E1. Now the transition is from higher level to lower level and so the difference in energy is being emitted and this emission we call it as spontaneous emission. Spontaneous always means on its own without the aid of any stimulus. So this process of emission of light is called spontaneous emission. Then we have stimulated emission. We will try to understand why do we have to go for stimulated emission and what happens with spontaneous emission. Now, a photon having energy h nu 12, that is the difference between E2 minus E1, impinges on an atom present in the excited state. Now, what we are going to do here is the atom is now say in the excited state before it makes a transition to the ground state. So, the atom is in E2. E2 is the excited state. So, the atom is in the excited state and this is E1. So, once the lifetime is over, this atom spontaneously comes to the ground state by emitting the difference in energy. We were calling it spontaneous emission, but the energy that is emitted is not giving us laser because it is not coherent. It happens naturally and there may be different frequencies because it may occur at any time. So, it may go waste. Whenever the energy is emitted, it is not giving us a sharp beam or a unidirectional beam. So, it is not producing laser. So, to get laser, what we do is we will have to stimulate it. When the atom is still in the excited state, before the lifetime is over, we try to stimulate it with an external stimulus, that is with a photon. So, what should be the energy of the photon? E is equal to h nu 12. Now, this atom is stimulated with the help of this photon. Now, what happens after stimulation? We are going to see. Now, when the stimulus is given, this atom comes to the ground state. So, when it comes to the ground state, what happens here we see is a difference in energy is again emitted. So, what is this? This represents the incident photon. This is the incident photon and this is because of the difference in energy, that is the emission. What we are seeing here is the emission or the emitted photon. And when these two are in phase with each other, we get a coherent beam. So, and it satisfies all the characteristics of laser. So, what we try to understand here is, even before the lifetime is over, we are trying to stimulate it with the help of an external photon. So, it is stimulated to make a transition to the ground state. And because of this stimulation, it gives off a photon of energy h nu to 1, means the difference in energy is being given out. So, the emitted photon is in phase with the incident photon. So, if you are representing this as h21, this may be the incident photon and this may be the emitted. So, but what we see here is these two are coherent. They are coherent, and this type of emission is known as stimulated emission. We are calling it as stimulated emission. Now, we will see the other terms that are involved. Lifetime means the time for which the atoms can stay in an excited state. We call it as lifetime. Now, what we have seen here is the ground state, E1, and then another state. We have only seen two levels, E1 and E2. E1 we are calling as ground state, E2 we are calling as excited state. So once we supply energy to the atoms in the ground state, they are excited. So the time for which they can stay here in the excited state, we are calling it as lifetime. Suppose if there is another state, we have another level E3, these atoms may come and stay here, and the time for which they can stay in this state, we call it as the lifetime. But there may be a difference in the time for which they stay, which we are going to discuss. Now, we are going to see the metastable state. It is an excited state in which the atoms can stay for a relatively longer time. Now, when I am talking about excited states E2 and E3, suppose in E2, the atoms can stay for 10 power minus 9 seconds. This is the lifetime of the atoms in the excited state E2. So, after 10 power minus 9 seconds, these atoms make transition to the lower level on their own without the stimulus, spontaneous emission. Now, when these atoms come here after transition, they stay here in E3, and the time for which they stay here is relatively more when compared to E2. So, they may stay for 10 power minus 3 seconds in E3. So, now if you compare the states E2 and E3, in E3, the atoms are staying for a relatively longer time. So, E3 will become the metastable state. So, that is what the metastable state defines. It is an excited state in which the atoms can stay for a relatively longer time. That we are calling it as metastable state. Now, in metastable state, what happens? Excited state with relatively more time is called a metastable state, and this is the necessary condition for population inversion. Okay, means population inversion occurs only in the presence of a metastable state. So, this is the necessary condition. Let us try to understand. Now, this is the ground state where initially the atoms will be in the ground state, and when we are exciting, means when we are supplying an external energy, these atoms will go to the excited state. We will call this as E1, this is E2, and this is E3. Now here, in this case, the lifetime is only 10 power minus 7 seconds. After 10 power minus 7 seconds, these atoms have to come to the lower energy level. So, there is a de-excitation we call. And in this state, the atoms can stay for 10 power minus 3 seconds. So, which we are calling it as metastable state. So, this is the ground state. After excitation, they go to the excited state. They cannot stay there for a longer time. So, they make the transition to the lower energy level where the period of stay is relatively longer. And that is why we call it as metastable state. And this state is very much important for getting laser, because when we discuss about population inversion, we will try to understand why this is a very important condition for population inversion. Now, coming to population inversion. First of all, let us understand the term population. Population here represents the number of atoms that are present in a particular level. Okay. Now, if N1 is the number of atoms present in the ground state E1, so I will call the population in E1 is N1. N1 simply represents the number of atoms present in the ground state. So I can say that is the population of N1. And N2 is the number of atoms present in the excited state. So if you see here, I will say this is the ground state E1. This is the excited state E2. And these are the atoms that are present in the ground state. I say the population is N1 here. And there are very few atoms in the excited state, that is N2. Now, usually when you see the number of atoms N1 that is present in the ground state is larger than the number of atoms N2 present in the excited state. You can see from the figure here, we have very few, that is only one is seen here in the excited state. That is the number of atoms in the excited state is very less when compared to the number of atoms in the ground state. Now, the existing condition, we can write it as N1 greater than N2. What does N1 greater than N2 represent? The number of atoms in the ground state is more than the number of atoms in the excited state. Then, by using pumping mechanism, we can make N2 greater than N1. So, why we need to have N2 greater than N1? Why should we go or make N2 greater than N1? That is what we need to understand. So, when the atoms are in the ground state, we need to supply energy and pump them into the excited state, because only when they are in the excited state and we supply energy in the excited state to make a transition to the ground state, the difference in energy is being emitted and we get laser. So, it is very much important that the number of atoms in the excited state is more than the number of atoms in the ground state. But how do we make the number of atoms in the excited state more than that in the ground state? That is by using some pumping mechanism. We use some pumping mechanism. Pumping is nothing but the process of sending the atoms from lower energy level to higher energy level by using some energy source. So, the process of making N2 greater than N1, we are calling it as population inversion. Actually, if you see, N1 has to be greater than N2. N1 will be greater than N2. The number of atoms in the ground state is more than that in the excited state. But to get laser, what is the condition that is required? The condition that is required is N2 should be greater than N1. So, how do we make N2 greater than N1? We are using some pumping mechanism and we are going to pump the atoms which are there in the ground state into the excited state. So, when we are seeing these two conditions, N2 greater than N1 means we are making this inverse. So, we are calling this condition as population inversion. So, population inversion means the process of making N2 greater than N1. How are we making N2 greater than N1? By pumping. So, what are the conditions for population inversion? The system should possess at least a pair of energy levels. At least minimum 2 energy levels have to be there, where E2 is greater than E1. They cannot be at the same level. E2 should be definitely greater than E1. That is separated by an energy equal to the energy of a photon. When we are talking about the energy of a photon, E is equal to h nu. So, when we are stimulating the atoms which are in the ground state with the help of a photon, they go to the excited state. So, the difference in the energies between these two levels should be a minimum equal to h nu. That is the energy of a photon, because we cannot supply half photon or a fraction of a photon. So, what is the energy of the photon? At least that minimum energy difference has to be there between the two levels. Now, the next condition is there should be a continuous supply of energy to the system so that the atoms may be raised continuously to the excited state. Now, what we are doing here in population inversion, we are sending the atoms or we are pumping the atoms from the ground state to the excited state. So, for pumping, we need to supply energy. So there should be a continuous supply of energy, because once the atom goes to the excited state, they cannot stay there for a longer time. After the lifetime is over, they come to the ground state. And if there is no energy supply, they will remain in the ground state. That is why we need to have continuous supply of energy so that the atoms will undergo transitions. Now we are going to see 3-level laser system. Till now we were discussing only 2-level. So what is the advantage of this 3-level laser system we are going to see? In 3 levels, the first one, the level 1 here is E1, which is the ground state we call. Then here we are calling it as level 2. Maybe we will say this is E2. And this is level 3, which is E3. Now initially, where are the atoms? The atoms are in the ground state. Atoms or electrons, what we call, they are in the ground state. So the number of atoms which are there in the ground state, we are denoting it by N1. The population here is N1. Now with the supply of some energy, when the energy, this is called excitation. So by supplying the energy, which is equal to, here I'll write as H nu 1, 3. The difference in energy when we are supplying, they are getting excited to the higher energy level. But in this, they cannot stay for a longer time. Before you stimulate, they will make a transition to the ground state, and whatever transition is happening, it is spontaneous emission. And in spontaneous emission, we do not get a coherent beam or a laser beam. All the energy is being wasted. So if we have another state, which we call it as metastable state, where the lifetime is relatively longer than E3, then what happens? These atoms may come to this, where they stay for a relatively longer time, and we have sufficient time to stimulate them and make them transition. So when the transition happens from the metastable state to the ground state, whatever the energy that is incident and whatever the difference in energy is being emitted. So we will call this as stimulated emission, and we will have a laser burst. So that is the greatest advantage of having a metastable state. If there is no metastable state, if no metastable state exists, these atoms from the excited state directly come to the ground state. It may be non-radiative, or we do not get any energy, useful energy from that. But if there is a metastable state in a 3-level laser system, what we see the advantage here is the atoms can stay for a relatively longer time, and when we stimulate them with the help of an external photon, then there is a transition where we get laser burst. Now, what are the pumping mechanisms? The population inversion can be achieved by a number of ways. We have discussed population inversion, means making the number of atoms in the excited state more than in the ground state. Means we have to just pump the atoms from the ground state to the excited state. So what are the mechanisms we are using to pump these atoms to excited state? So the first one is optical pumping. Second one is electrical discharge. Third is inelastic collision of atoms. Then we have thermal pumping and chemical reaction. So we are going to discuss one by one now. First, we'll see what is optical pumping. So in optical pumping, it's a process in which the light is used to raise the atoms from lower energy level to higher energy level. Optics is itself related to light. So what we are doing here is we are supplying the energy in the form of light. So light is used to pump the atoms from lower level to higher level. That is why we are calling it as optical pumping. And it is commonly used in laser construction to pump active laser medium, so as to achieve population inversion. So this is the most commonly used pumping mechanisms, where we use it on the active laser medium so that the atoms can be pumped to higher energy level. Now the second one is the electric discharge. So electric discharge refers to the flow of electrons or electric current through a gas or a liquid or a solid. We may take the active medium as a gas or liquid or solid. Okay, in this method of pumping, the electric discharge acts as the pump source. So what is the pump source here? The electric discharge is the pump source. A high voltage electric discharge, that is, electric discharge is nothing but the flow of electrons or the electric charge, and the flow of electrons gives rise to electric current. So when this is passed through the laser medium or a gas, then what happens? They gain sufficient energy. The atoms which are present in the ground state, they gain sufficient energy to go to the excited state. So the intense electric field accelerates the electrons to high speeds and they collide with the neutral atoms in the gas. So what is the mechanism that is happening there in electric discharge? So what happens here? The electrons in the lower energy state gain sufficient energy from the external electrons. The electrons due to the electric discharge, okay, these are the external electrons and they are gaining the sufficient energy and jumping into the higher energy state. And this method of pumping is used in gas lasers. Mostly we are using this method in gas lasers such as argon lasers. The third one is inelastic collision of atoms. So how does pumping occur due to the inelastic collision? When we say inelastic, means the energy may not be conserved. Some amount of energy may be lost. That is why we are calling them as inelastic collisions. So what happens in inelastic collision? Just like in electric discharge, there is also a high voltage electric discharge which acts as a pump source. Here also we will take as a high voltage. And in this method, we take a combination of two types of gases. We are using two types of gases and we are naming them as X and Y. Let the gas one be X and the other one be Y. And now the excited state of the gas X is represented by X plus and the excited state of gas Y is represented by Y plus. And usually the gases, the excited states may be at the same level. After excitation, they may have the same excited states which will help them in attaining the population inversion. Now, when high voltage electric discharge passes through the laser medium, we are sending the electric discharge through the active medium which is having these two types of gases. We are always considering it two types of gases, X and Y. So what happens when the electric discharge passes? The lower level energy electrons in the gas will move to excited state X plus. We have named it as X plus. Okay. And similarly, the electrons in the gas Y will move to the excited state Y plus. So we have gas X, we have gas Y. And the excited states we are denoting the excited states by X plus and this is Y plus. So when the discharge passes through the gas, these electrons of gas X may get excited to X plus and the atoms or the electrons of gas Y may get excited to Y plus, and these both may be at the same level. Now, initially what happens? The lower energy state electrons in gas X or the atom X get excited to X plus due to continuous collision with electrons. So, which atoms are getting excited first? In X. They are getting excited because of the collision. When this electric discharge is there through the active medium, they collide with the atoms which are there in the ground state. And now the excited electrons in gas X plus collide with the lower energy state electrons in gas Y. So here what we are seeing here is once the X gets excited, these electrons will collide with the lower energy electrons in Y. Means sometimes what happens here is if you have X and there is X plus, after gaining the energy, from the photon, they may go to the excited state. And this is the Y where we have certain atoms. Now these atoms which are there in the excited state, because they may not be able to stay for a longer time, and because of the emission also, they may collide with the atoms in the ground state of Y. And as a result, the lower energy state electrons in gas Y will get sufficient energy and jump to the excited state. So now these atoms will gain sufficient energy and they go to the excited state Y+. So this method is used in helium-neon laser. We are using two gases here, helium and neon. Whatever X gas we are calling here is helium and the gas Y is neon. So when we discuss about helium-neon laser, we will again discuss about this inelastic collision of atoms. Now the next one is thermal pumping. Thermal is always related to heat. Thermal means thermal energy is heat energy. Okay. Sometimes we achieve population inversion by heating the laser medium. Means in thermal pumping, heat acts as the pump. Because for the ground state atoms, we need to supply energy. And the energy we are supplying here is in the form of heat. So the energy source is here heat. So in this method, the population inversion is achieved by supplying the heat into the laser medium. So thermal pumping, what we need to understand, the population inversion is achieved by supplying the heat. Now when heat energy is supplied to the laser medium, the lower energy state electrons gain sufficient energy and they jump into the higher energy level. This is the basic thing we were talking about in pumping. Pumping itself means the process of jumping of the electrons or the atoms from lower energy level to higher energy level. So by doing that, what is happening? There is what we call as population inversion. So the process of achieving population inversion in thermal pumping is similar to optical pumping or electric discharge method. Except in this method, heat is used as a pump source instead of light or electric discharge. So in optical pumping, we have used light as a source, and in electric discharge, we have used the high voltage. So in both the cases, what we have seen, by the energy we are supplying, the atoms in the ground state are gaining the energy and they are going to the excited state. So in thermal pumping also, in a similar way, they absorb the energy. Only thing is the energy given here is the heat energy. So by absorbing the heat energy, the atoms will go to the excited state and population inversion is achieved. The next one is chemical reaction. So what happens in a chemical reaction? If an atom or a molecule is produced through some chemical reaction and remains in an excited state at the time of production, then it can be used for pumping. Now, for example, we take the hydrogen fluoride molecule is produced in an excited state when hydrogen and fluorine gas chemically combine. There is a chemical reaction that is occurring here. We are taking two gases when hydrogen and fluorine combine together chemically, and because of this chemical reaction, they are remaining in the excited state. The remaining in the excited state means already the pumping has occurred. So the number of produced excited atoms is greater than the number of normal state atoms, and this is what we call as population inversion. If the number of atoms in the excited state is more than that in the normal state, we are calling N2 greater than N1. And this is what we are calling as population inversion, because population inversion is a must to get laser. So how we are achieving it? With the help of chemical reaction. So in chemical reaction, what we are seeing, these atoms, because of chemical combination, they remain in the excited state, thereby achieving the population inversion. So the example here is H2 plus F2 will give us 2HF. So in this chemical reaction, what is happening? The hydrogen and fluorine molecules chemically combine and produce hydrogen fluoride, which is in the excited state. So when they are in the excited state, as I said, the condition for population inversion is already achieved. Now the next thing we are going to see is the lasing action. Whenever we need a laser, there are different steps that are involved and we call it as lasing action. So the first one is pumping. We have already seen pumping. And the next one is population inversion. And the third one is stimulated emission of radiation. We have discussed all the terms and the phenomenon separately. Now all these three put together will give us the lasing action. So what is that lasing action? We are going to understand. So in pumping, what we have seen, it is the process of sending the atoms from lower energy level to higher energy level. Because the atoms are in the ground state, we need to send them to the excited state. So to send them to the excited state, we need to supply energy. And this process of supplying the energy and sending them to the higher energy state, we are calling it as pumping. And we have also seen different pumping mechanisms depending upon the type of laser. So for ruby laser, we use optical pumping. Optical is related to light. We are using light as a source and pumping. So in ruby laser, optical pumping we use. And in helium neon laser, the pumping mechanism is electric discharge, because these atoms, helium and neon, are gaining the energy from the electric discharge and then they are pumped into the higher energy level. And in semiconductor laser, we use another method called direct conversion. And in CO2 laser, that is a carbon dioxide laser, the mechanism we use is chemical reaction. Whenever there is a chemical reaction, the atoms are already in the excited state. That is therefore achieving population inversion. Now then the population inversion can be achieved easily with the presence of a metastable state. We have already discussed about the metastable state. If you need population inversion, if there is a metastable state, then the process becomes very simple. So instead of having only a 2-level laser, if we can go for 3 or more than that, means a level in which the atoms can stay for a relatively longer time, the emission becomes very easy. Then comes the stimulated emission. The photons that are produced by stimulated emission are in phase and they produce coherent light. So only in stimulated emission, if the atoms are coming down on their own, they will not be able to emit laser. They will not give coherent light. So what we are doing here is stimulated emission. By supplying the energy, by stimulating the atoms that are present in the excited state, we are stimulating them with the help of an external photon so that they make transition into the lower level. And that is what we are doing in stimulated emission. Now, in lasing action, what we are seeing here is 3 things. The first thing we have seen is pumping. Pumping here means the atoms which are in the low ground state, with the help of an incident photon, are supplying some form of energy, any pumping mechanism we use, and we send them to the excited state. So the atoms are being pumped. So what we see here is there is a population inversion. What is population inversion? The number of atoms in the excited state N2 is greater than N1. So population inversion is achieved. Now when this population inversion is there, what happens? If you stimulate it with the help of an external photon, then there is the radiation that is emitted. And the photons that are produced by stimulated emission will have a definite phase relationship, producing coherent light. So the first one is the pumping, and the second one we need is the population inversion, and third one we need is the stimulated emission radiation. All these 3 steps will give rise to lasing action. Now in a laser system, what do we have? So because whenever we are discussing different types of laser, either a ruby laser or a helium neon laser, any laser system, it consists of 3 basic parts. So the first one is the active medium. What is an active medium? It consists of a set of energy levels to support the laser action. For example, if you take ruby laser, chromium ions will be the active laser particles. There should be an active medium which takes part in lasing action, and that we are calling as active medium, or we also call it as a gain medium or the laser medium. Then we need an energy source, that is for pumping, because the atoms which are in the ground state has to go to the excited state to achieve population inversion. So we need an energy source. Any type of laser you take, so the first thing is the active medium that is required. The second one is the energy source, and the third one is optical cavity, or we also call it as resonator. So what does this optical cavity do? So it will introduce the optical feedback to maintain the gain of the system and overcoming all the losses. So depending on the type of system, that optical feedback is provided with the help of dielectric mirrors or polished surfaces, polished coated ends of a crystal rod or a cleaved crystal surface. So in an optical cavity, what we have generally is, this is a cavity. You will have mirrors on both the sides and they are polished. So why polished? Because there may be reflection. There will be an optical feedback. They are polished. How they are polished, we are going to discuss. Now, if you see, this is the cavity. I say this is the optical cavity where we take the active medium. But this is kept enclosed in a tube which has two mirrors at the end. Okay. So these are dielectric mirrors or polished. Okay. So what happens because of this? There will be an optical feedback, or we call it as a resonance that happens, because of which they gain the energy and we get laser. Now, if you see the diagram, so this is the laser medium we are talking about. The part one is the laser medium, and the second one is the pumping mechanism we need, and the third one is the optical cavity. This is the cavity in which we are taking. So there are two mirrors. This is one mirror, rear mirror, where the reflection is 100%. And here this is a front mirror where the reflection is 95%, so that we may get the output laser beam. So if you see any laser system, these are the three basic components. The first one is the active medium or the laser medium. And the second one is the pump source or the energy source. And the third one is the resonator or the cavity, optical cavity. Now, when you see the type of lasers, we have different types of lasers. Gas lasers we have, helium neon laser and CO2 laser. Then we have solid state laser. In solid state laser examples, we take ruby laser and glass laser. And also we have semiconductor lasers, which are homojunction lasers and heterojunction lasers. Then we have chemical laser, which is a hydrogen fluoride laser, which we have seen in the chemical reaction. Chemical pumping, we have discussed about this hydrogen fluoride laser. And also in excimer laser, we have using fluorine. And in the next classes, we are going to discuss one gas laser, that is helium neon laser, and one solid state laser, that is ruby laser. Thank you. See you in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.